Okay, so good evening everyone. I am Shivani Dhop and I welcome you all to the week 7 tutorial for the course of Introduction to Wireless and Cellular Communication Systems. So like every week, this week's tutorial will be divided into two parts. The first part will be a brief recap of what content was covered in week 7, not in detail but yeah, overview of what all things were covered just for a quick thing, followed by the questions which are related to the content that was covered in this week, which shall help you in solving your assignments. If you have any questions at any point of time, you can feel free to stop me at that point. Please unmute yourself and ask the queries because the chat box might not be visible to me. Okay, so let's quickly start with the recap of week 7 content. So this week we started looking at the models which help us to figure out how to generate time correlated channels, or basically for simulation purposes how to generate time varying channels, time varying relay channels. And for that we looked at four methods. The most famous one from all of this is the Jake's method, but the first thing that we looked at was the Clark and Gans method, in which we said that this is a filter based method in which we generate two complex Gaussian random variables and pass them through the filter whose Fourier transform is under root of your temporal correlation, or the Fourier transform of your Bessel correlation function that we had derived earlier. And this we do in time domain. The second approach that we looked at was the Smith's method. In Smith's method, this is also a filter based method. But instead of looking at filtering operation in time domain, we said let us do the same thing in frequency domain. So basically what we do, we take the Fourier transform of your AWGN, your uncorrelated noise, and then we also take the Fourier transform of your filter, the same filters that we had here, and we multiply them in frequency domain and then invert them. Now the good thing that we can do here is we can generate Gaussian random variables in the frequency domain as well, instead of generating them in the time domain. Just we need to take care of the symmetry of the Fourier transform while doing that. After that, we looked at the Jake's method. I won't reproduce those equations right now here because just for the sake of completion, we'll take an example for different values of system parameters and see how to simulate this Jake's method. But just to give a glimpse, this is the method where we used oscillators and with random phases to generate the time correlated channels. We'll see how exactly we do. And a modified version of this Jake's method is this Dent's method. And this Dent method is, as I said, it is a little bit modification to Jake's method. And it basically helps you to generate multiple streams which are uncorrelated, but each stream among themselves is time correlated. So basically you can have z1 of t stream for all t, then you will have z2 of t for all t. So this is time correlated, this is also time correlated, but z1 of t1 and z2 of t2, these are uncorrelated. uncorrelated or independent. Okay, these were the four methods that we looked at. And after that, we started a very important concept in wireless communication, which actually helps you to benefit from the uh, fading that is available to you to improve your system performance, and that is called as a diversity. So what we said is, let's say we have an antenna at the transmitter side, and let's say we have multiple antennas at the receiver side. So some 1, 2 and some NR antennas you have at the sorry m we let's stick to the notations. You have some m number of antennas at the receiver side, and you have the channels between them, zm, z1, and so on. And now you will be receiving the same signal at different antennas. Now how to combine that at the receiver end, that's what is known as a diversity. Okay, and this diversity is most useful when we have independent channels. So for that we looked at three cases. The first one was the selection combining. So in selection combining, what we say is, for each of these corresponding antennas, you have different channel gains, and for those channels you will see different instantaneous SNRs. So you select that particular antenna which has the maximum SNR. So okay, yeah. So the selection combining says that select the antenna with the best SNR. So this gamma selection combining, this is gamma is the instantaneous SNR, is basically max of the SNRs of each antenna. And we also saw the statistics of this particular thing. After that, we said that we anyway have large number of antennas. Then why to discard the information that we are receiving at every antenna? Let us be little bit clever and use the information that we have at all the antennas. So what we said, let's say r1 of t, let's say for now this capital M is equal to 2, and we have r1 of t, which is a signal received at first antenna, and r2 of t is the signal received at the second antenna. Then let us combine and get r1 of t as e power minus j phi 1 r1 of t plus e power minus j phi 2 into r2 of t. So here what is happening is the z1, okay, so let's be clear. We had this r1 of t as z1 s of t plus eta 1 of t, where eta 1 of t is the AWGN noise, and r2 of t is z2 into st plus eta 2 of t, and here your zi is basically alpha I into e power j phi I. So by doing this particular operation, what are we doing? We are basically undoing the phase rotation that this particular channel is doing. So after multiplying this r1 by e power minus j phi 1, you'll be left with only its magnitude, that is alpha 1. Okay, so what happens is, we are sending some particular constellation that gets rotated by the phase of the channel, and now we are undoing that phase when we are multiplying it. We'll get back to this thing in detail when we come again to this. And the last one that we looked at was this optimal combining, we said that instead of doing this co-phasing, we know this phase undoing is helping, but will it help if we also play with the magnitude? So for optimal combining, we started with combining our channel, combining our signals received at the antennas with different weights, which we said gi into ri of t, and then we showed that gi equal to zi conjugate upon sigma ni. This is the weight optimal weight which maximizes the SNR. So this is the optimal combining, and for this particular situation, we saw that the SNR, that is gamma MRC, was coming out to be the summation of the signal to noise ratios across all the antennas, like this. Again, selection, co-phasing and optimal combining SNRs will again revisit in a detail. I want to give few more intuitions of what exactly these are giving and how these both are different and why this particular thing is giving you a better SNR. Any questions? Okay. If there are no questions, then let me move on to the questions that I have planned to cover today. So this is the first question. So it says that given the channel coherence time and coherence bandwidth are 20 microseconds and 100 kilohertz respectively, 64 QAM modulation is used for communication to achieve 5 Mbps throughput. Classify the channel based on the time and frequency selectivity. Okay. So what is the information given to us? So the information that is given to us is, the first thing is the coherence time of the channel, which is TC, which is 20 microseconds. And then what is given to us is coherence bandwidth, which is B subscript C, which is equal to 100 kilohertz. Then the system throughput, or basically the data rate, is 5 Mbps. And the fourth information given to us is the constellation, that is 64 QAM, which means this is a 64 QAM constellation, which means the number of symbols or number of bits per symbol are log of 64 to the base 2, which comes out to be 6. So this is the information that is given to us, and what do we need to do? We need to classify the channel based on the time and frequency selectivity. Okay. So in last week's lectures, we had seen or we had drawn a diagram which was something like this. So here we had symbol duration. This was a time axis, and the vertical one was the signal bandwidth. And then we had drawn, divided this into 4 parts, like this and like this. And the demarcating point on the time axis or duration axis was the coherence time, that is TC. And on the vertical axis, that is the bandwidth axis, was the coherence bandwidth, that is BC. So what we said was, if the symbol duration is less than if the symbol duration is less than the coherence time, then the signal is time flat. And if it is less than, and if the signal bandwidth is less than the coherence bandwidth, it is frequency flat also. Then if it is having a symbol duration still less than, if the symbol duration is still less than the coherence time, but the signal bandwidth is more than the coherence bandwidth, then it is still time flat, but now frequency selective. Now suppose you have symbol duration higher than your coherence bandwidth, then you are having a channel which will be time selective, and if its bandwidth is less than the coherence bandwidth, it is frequency flat. And similarly, if its symbol duration is still more than the coherence time, and the signal bandwidth is now higher than the coherence bandwidth, then it is both time and frequency selective. So the question that is asked to us is, we want to figure out in which particular quadrant we fall given these four information. Okay. So what we need to find out is, okay, so on what basis or what pieces of information we can figure this out? We can figure this out when we know the coherence bandwidth, which is given to us, then coherence time, which is also given to us, and then two more things we need, which is the symbol duration and the signal bandwidth, which is not given to us directly, but which we want to find out through this particular uh, given information. Okay, so let's try to do that. So the rate that is given to us, so rate that is given to us is 5 Mbps. So from this, the symbol rate is your bit rate. This rate is basically your bit rate, divided by the number of bits per symbol, which is equal to 5 into 10 raised to 6 divided by number of bits per that is 6, which is equal to 5 by 6 into 10 raised to 6. So this is also the bandwidth. So this is also your signal bandwidth, and your coherence bandwidth was given to us as your 100 kilohertz. And obviously this is less than your signal bandwidth, which means that your signal bandwidth is higher than your coherence bandwidth, which means that your channel is frequency selective. So frequency selectivity is sorted. Now, what is the symbol duration? So your symbol duration is 1 over your symbol rate, that is 1 over 5 by 6 into 10 raised to 6, which is 6 by 5 into 10 raised to minus 6. This is equal to 1.2 microseconds, and your coherence time is given to you as 20 microseconds. So now your symbol duration, I'll abbreviate it as or denote it by TS. So your TS is much less than your TC. So if the signal duration is much less than your coherence time, which means that you fall in this region, and therefore you are having a time flat channel or slow fading, one and the same thing. You have time flat or you experience slow fading. Okay, so based on the information given to us, we see that the given channel is coming out to be frequency selective and time flat for the given case. Any questions? Okay, if not, then I'll move on to the next question. Okay. So for the following Doppler frequency, find the number of FFT points required for the Smith's method. Assume the symbol rate as 24.3 kilosymbols per second and 8 times sampling frequency. 8 times oversampling. So what is given to us is the symbol rate, which is basically 41.2, sorry, yeah, this is 24.3 kilosymbols per second. From this, you can get your symbol duration, which is basically 1 by Rs, which is equal to 41.2 microseconds, and from this you can get your sampling frequency, and since you have 8 times oversampling, 1 over 8 over Ts, which comes out to be equal to 194400 hertz. I'm not getting into details of these calculations because this was done in the class, but this is the sampling frequency that we are dealing with. Okay, so now what we need to find is the number of FFT points in Smith's method is given by the sampling frequency divided by the separation. Uh, so here delta F is the frequency separation in your FFT that you are going to do. Okay, and what we are saying is in the signal bandwidth we want 21 points, 21 FFT points between minus FD and FT. This is the standard thing that we had looked earlier also. Okay, so now let us try to do it in these three cases. So the first case is given to us as your FT as 200 hertz, and the number of points that we want are 21, which means that your delta F will be FT upon the number of points, that is 21 minus 1, that is 200 divided by 20, that comes out to be equal to 10. Sorry, it will be 2 times FT. So this is 400 upon 20, that is 20. Okay, therefore number of FFT points for 200 hertz comes out to be equal to your sampling frequency, which is 194400 divided by 20, and this comes out to be equal to 9720. So these many points you require to get a sufficient resolution in your FFT so that it resembles your Fourier transform. Now this was for 200 hertz. Now if I have 500 hertz, then the separation in frequencies will be 2 times FT upon 21 minus 1, that is 1000 yeah, 2 times FT 1000 divided by 20, which comes out to be equal to 50. So therefore number of FFT points for 500 comes out to be equal to 194400 divided by 50, which is equal to 38808. And finally we have the third one, that is 50 hertz, and for this your frequency separation is 2FT divided by 21 minus 1, that is 100 divided by 20, which is 5. Therefore NFFT, number of FFT points for 50 hertz Doppler, comes out to be 194400 divided by 5, which is 38880 points. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay. So this question says that suppose the maximum Doppler in the um, in the channel is 150 hertz, then find the expressions for the Jakes simulator. Okay, so for the Jakes simulator, So how does your Jake simulator look? So for Jake's simulator, we generate the channel. The channel is given by zt equal to zr of t plus j times zi of t, where zr is the real part and zi is the imaginary part. Where the zr of t is given by, we had seen that is given by 1 over some scaling factor into 2 times summation n equal to 1 to n naught cos beta n cos of 2 pi fn t plus phi n plus under root 2 cos alpha into cos of 2 pi fdt, and your imaginary part zi of t is 1 over scale factor 1 into 2 times n equal to 1 over n equal to 1 to n naught sine of beta n cos of 2 pi fn t plus phi n plus under root 2 sine alpha into sine 2 pi ft. Okay, so these are the two expressions. And in the class we said that, or we saw that we'll be choosing alpha equal to 0, or when we choose alpha equal to 0, we can have our beta n comes out to be equal to pi n upon n naught plus 1, and these fn's are basically fd cos of 2 pi n by n, and the fd that is given to us is basically 150 hertz. So this 150 into cos of 2 pi n by n, and this n can basically take the value as 4 n naught plus 2, or rather n naught will be related to, n is the number of samples that you want, so your n is basically related to your n naught, your n naught is related to n as n minus 2 by 4. So this means that your n naught has to be equal to n minus 2 by 4. So now if I substitute everything back in these equations, yeah, and one more thing, in this setting we had seen that the scale factor 2 came out to be equal to under root of 2 times n naught, and sorry, and the scaling factor 1 came out to be equal to under root 2 times n naught plus 1. Okay, so now if we substitute these equations in this, then the zr of t, that is the real part, comes out to be equal to 1 over scale factor 2, that is 1 over under root 2 n naught summation, I have a bracket here, 2 times summation little n equal to 1 to capital N naught cos beta n. Beta n is pi n over n naught plus 1. So cos of pi n over n naught plus 1 into cos of 2 pi fn t plus phi cos of 2 pi fn is basically 150 into cos of 2 pi n by n fn t plus phi n, plus we have under root 2 alpha, alpha is 0, so cos alpha is 1, so plus under root 2 plus you have your cos 2 pi ft, and ft is again 150 And then you have zi of t, which comes out to be equal to under root 2 times n naught plus 1 2 times summation n equal to 1 to n naught. We have sine beta n, so sine pi n over n naught plus 1 into same term cos of fn, that is 150 cos 2 pi n by n t plus phi n plus root 2 sine alpha, alpha is 0 so that term goes to 0, plus sine 2 pi into ft t. And these phi n's will generate uniformly from 0 to 2 pi. Is it clear? Any questions? I just took this example to just give you a flavor of how you are going to come up with those equations which are required to get your to get the expressions to run your simulator. This is just a repetition of whatever was covered in the class. Any questions till now?
No, madam.
Yeah, just a minute. Okay, if there are no questions, then let me move on to the next question. Okay, so in the class, when we were discussing how this Jake's model takes us to the Bessel correlation model. So at that time we said that we'll find out the time average of this ZR, ZI, then ZR square, ZI square, and also ZR, and also their um, and also to find their autocorrelation, like expectation of Z of t into Z conjugate of t plus delta t. And for all of these, we wanted to find the time averages. And for time averages, we would be getting the terms or terms to find time averages of products of cosines of different frequencies or same frequencies. So how to figure that out? So just to understand those concepts, I have brought it, and just to show how why they come out to be 0 or let's say 1 by 2, I have brought these things here. Okay, so the first one that is given to us is cos of 2 pi f1t into cos of 2 pi f2t, and this basically you can apply the cos b formula, and we can write this as half of cos of 2 pi f1 plus f2t plus cos of 2 pi f1 minus f2t. Okay, and we want to find the time average of this particular thing. So the notation that we used was time average of this thing. Leave it. Let's say I denote this by x of t, x1 of t, let's say. So I want to find the time average of x1 of t, which is basically half of the time average of cos of 2 pi f1 plus f2t plus half of the time average of cos of 2 pi f1 minus f2t. Okay, so now we let us understand what exactly is this particular thing. So when we want to find the time average, so we have this cosine function. It extends infinitely in both the directions. So we focus on one period like this. So what we will do is first, let us do it in general. So suppose we have cos 2 pi ft. This is your cos 2 pi ft, and we want to find the time average of this thing for any frequency that is available. So what we will do for this, we'll do limit capital T tends to infinity, and let us just fix it to minus t to t, and here your t is basically some integer multiple of your 1 over f, like this, something like this you have. So then you will have cos 2 pi ft dt. So this is limit t tending to infinity, and then you will have, am I doing some mistake? No, you'll have sine 2 pi ft upon 2 pi f from minus t to t, and let me add a page. So this thing is basically limit t tending to infinity. You will get sine of 2 pi ft minus sine of 2 pi f of minus t, which is equal to limit t tending to infinity. Now this t is your 1 over k over f, which means that this thing comes out to be equal to 0, and this thing comes out to be equal to 0. So this is 0, which comes out to be equal to 0. So basically what is happening is, if you cycle or if you move along the one period or one cycle of your sinusoid, so the average, or you integrate it, it comes out to be 0. So basically you're averaging over an entire range of time, and you're basically just keeping on adding zeros multiple times. So therefore this time average of a sinusoid from minus infinity to infinity comes out to be 0 for any phase. Even if you can also try out the same thing when you have sine 2 pi ft. Okay, so in similar way, we can show time average of sine 2 pi ft is also equal to 0 for any frequencies. Now let's go back to the example that we had. In our case, we had x1 of t to be equal to half of the time average of cos 2 pi f1 plus f2t plus half of the time average of cos of 2 pi f1 minus f2t. Okay, now this particular thing is a cosine function with frequency f1 plus f2, and this is a cos with frequency f1 minus f2, and we saw that for any frequency this time averages come out to be 0. So this is half into 0 plus half into 0, so therefore this comes out to be equal to 0. Similarly, the second thing that we had was your x2 of t is basically sine 2 pi f1 t into cos of 2 pi f2 t. So in this we can apply the sin a cos b formula. So for this we'll get half of sine of a plus b, that is 2 pi f1 plus f2 t plus sine of 2 pi f1 minus f2 t. Okay, So this is what we are having right now, and therefore the time average x2 of t is equal to half of the time average of sine of 2 pi f1 plus f2t plus half of time average of sine of 2 pi f1 minus f2t, and this comes out to be equal to, again we have seen that for any frequency, so this one is a sinusoid with frequency f1 plus f2, and this is a sinusoid with frequency f1 minus f2. So the time average of this quantity and this quantity both are 0, so we get half into 0 plus half into 0, which comes out to be equal to 0. Similarly, we have the third case, and for this we have x3 of t as sine 2 pi f1 t into sine of 2 pi f2t. We can apply sin A sin B formula, and that comes out to be equal to cos of B minus A. So 2 pi f1 minus f2t minus cos of 2 pi f1 plus f2t. Okay, so we have this, and again the time average x3 of t is time average of cos of 2 pi f1 minus f2t minus cos of time average of cos of 2 pi f1 plus f2t with a half. Yeah, there is a half here, sorry. So again, this is we have seen that this particular quantity is 0. This is also 0. So this comes out to be equal to half into 0 minus half into 0, which is equal to 0. Any questions till this point? Okay. If not, then let me move on to the next question, the next part. So I have x4 of t as sine square 2 pi f1t, which I can write as 1 minus cos of 4 pi f1t divided by 2. So the time average x4 of t is equal to half minus half times time average of cos of 4 pi f1t. Half is a constant, you can take it outside, and this quantity here is equal to 0. This is basically a sinusoid or a cosine with frequency 2f1. So this comes out to be equal to 0. Therefore, this is equal to half minus 0, which is equal to half. Similarly, the last part of this question, that is cos square 2 pi f1t, which we can write as 1 plus cos of 4 pi f1t divided by 2. So therefore the time average x5 of t is equal to half plus time average of cos of 4 pi f1t. Again, we just said in the previous part that this quantity is 0. So this comes out to be equal to half plus half into 0, which is equal to half. So this is how you will be calculating the time averages when you have product of sinusoids with different frequencies or same frequency. So using these equations, you can now try out that derivation of your time correlation, temporal correlation coefficient before mapping it to Jake's, before mapping it to your Bessel function for your Jake simulator. Any questions till this point? Okay, if there are no questions, then let me move on to the next question then. Now we'll take up the questions which are, so maximum questions from now are related to your selection combining apart from one question. Your combining schemes, not just selection, but multiple other combining schemes. So the first question here says that derive the expression for the outage probability for the selection combining. So what do you mean by outage probability? Sorry, yeah. So probability of outage. This is basically probability that your instantaneous SNR falls below some threshold, that is gamma TH. So this quantity here is your instantaneous SNR, and this quantity here, this is basically your threshold. Okay, so this derivation we had done in the lecture, but still I want to repeat it once so that you are used to these kind of calculations. So for selection combining, your gamma selection or the instantaneous SNR is given by the max of the SNRs that are received at all the M antennas, like this. So therefore, your outage probability, which is probability that your gamma select is less than or equal to threshold, is basically your max of x1, x2 and so on till xm to be less than or equal to gamma th, or your threshold. So when we say that max is less than or equal to your threshold, which means that all of your SNRs are less than or equal to this threshold. Okay, for example, if you have such kind of things, or not in this way, let's say you have something like this, and this is your gamma th, and we want to find out the probability of this event, that this is your max or gamma select, which is max of all your gammas. So what is the probability that this gamma select is less than this threshold? So if this gamma select is less than this threshold, it means that if the maximum value is less than or equal to the threshold, all the other, all the other values should also be less than or equal to the threshold. So this probability is equivalent to the probability that your gamma 1 is less than or equal to your gamma th, your gamma 2 is less than or equal to your threshold, and so on till your gamma m is less than or equal to your gamma th. So what we have right now, So probability of outage is basically probability that gamma 1 is less than or equal to gamma th, then gamma 2 is less than or equal to gamma th, and so on till gamma m is less than or equal to your gamma th. So now suppose, so this is the outage probability if you have a very general case. Like I'm not specifying that your antennas are uncorrelated or anything like that. So this is the outage probability when you have no other information given to you. Generally we'll assume to be independent, but if they are not independent, then this is the outage probability. But now if all the M antennas are independent, sorry, if all the antennas are independent, then probability of outage is equal to probability is equal to the product of probabilities of I equal to 1 to m, probability that your gamma I is less than or equal to your gamma th. Okay, now this is the first thing. Second thing, if all if all the channels are Rayleigh fading, then your gamma I is an exponential random variable or a chi-square random variable with 2 degrees of freedom. Yeah, with mean gamma I. Then the PDF f gamma I is basically given by 1 over capital gamma I into e power minus little gamma I by gamma I, and its CDF is given by 1 minus e power minus gamma I by gamma I. And your CDF is basically the probability, okay, let's have this, yeah, probability that your gamma I is less than or equal to some gamma. Therefore, this equation that of probability of outage we can equivalently write as probability of I equal to 1 to capital M f of gamma I, that is CDF of gamma I evaluated at gamma th. So under this situation, the probability of outage comes out to be equal to product of I equal to 1 to capital M 1 minus e power minus gamma th by gamma I. So this is the most generic thing that you can have, and this is the outage probability. Now the third one is if all the antennas, let's say channels, are identically distributed, that is your gamma I is equal to gamma for all I in the range of 1, 2 and so on till capital M, then your probability of outage is equal to product of I equal to 1 to M 1 minus e power minus gamma th by gamma which is basically equal to 1 minus e power minus gamma th by gamma whole to the power m. Is it clear? Any questions? Okay. If there are no questions, then let me move on to the next question. So here it says that derive the expressions for the average SNR for co-phasing combining and the optimal combining. So we want to do it for co-phasing and optimal combining. So in the lecture when we were doing for co-phasing, we considered two antennas. Now let us try to generalize it for M antennas. So this derivation we will be doing for M antennas. Okay, so let us first start with co-phasing. So in co-phasing combining, what do we have? We have, as we had seen earlier, let's say we have a transmit antenna and we have M receive antennas, and each of these have channels ZM or Z2 or Z1. So Z1 to Zm are the channels for these antennas, and yeah, and what we will assume is this Zi is alpha I into e power minus j phi I, and this alpha I is Rayleigh distributed. Then expectation of this alpha I square is 2 sigma I square, and expectation of this alpha I, that is mean, is under root pi by 2 into sigma I. So these are the standard results for your Rayleigh distribution. Okay, so this is what we have here, and each of this each of this antenna will be receiving. Okay, so what we are transmitting is the symbol S of t, and at the antennas we'll be receiving the signals R1 of t, R2 of t, and R capital M of t, where R little m of t is given by your Zm into Zm into S of t plus eta m of t, where this eta m is Cn 0 sigma square or sigma nm square. Okay, so this is an additive white Gaussian noise with variance sigma nm square. So this is the setting that we are having. And when we want to do co-phasing, okay, so this is a general setup that we will be considering. Let us do co-phasing now. Let me move it here. Yeah, so for co-phasing, what do we do? So for co-phasing, we construct the signal R1 of t, which is e power minus j phi 1 into R1 of t plus e power minus j phi 2 into R2 of t, and so on till e power minus j phi capital M into R capital M of t, which I can write in a concise manner as summation little m equal to 1 to capital M e power minus j phi m into Rm of t. Okay, so now I can write this thing as So now I can substitute Rm of t in this. So what I'll get summation m equal to 1 to capital M e power minus j phi m into you have Rm of t, which is Zm, which I'll write as alpha m into e power j phi m. This is basically your Zm into s of t plus eta m of t. Now if I separate it out, so I'll have summation m equal to 1 to capital M alpha m into s of t plus summation m equal to 1 to capital M e power minus j phi m into eta m of t. Okay, so now this is your signal term, this is your signal term, and this is basically your effective noise. So I'll just write this as some eta effective of t, and let's say this thing is defined as Cn 0 comma sigma square. It is addition of your complex Gaussian random variables, linear combination. So this will also be a Cn variable, random variable with some variance sigma square, and we'll find out what this variance is in some time. So now your instantaneous SNR, that is your gamma co-phase, is basically magnitude of summation m equal to 1 to capital M, or rather this is just an amplitude, into alpha m square into the power of this thing. So let's say it is Es divided by your sigma square. Now let us understand what this sigma square is. Now your sigma square is basically expectation of magnitude of eta effective of t square, which is equal to expectation of magnitude of summation n equal to 1 to capital M e power minus j, we have used n, phi m into eta m of t square. Now this I can write as expectation of summation m equal to 1 to capital M e power minus j phi m into eta m of t multiplied by same quantity, but I just changed the variable, n equal to 1 to m e power minus j phi n into eta n of t, but conjugate. So this is equal to expectation of summation of m equal to 1 to n, summation of n equal to 1 to m, this is m, e power minus j phi m into eta m of t into e power minus plus j phi n into eta n conjugate of t. So now I can push in this expectation inside. For j phi n, expectation of eta m of t into eta n conjugate of t. Now these noises eta m and eta n are independent if m is not equal to n. So now there are two cases. First is if m equal to n, then your expectation of this quantity reduces to eta m of t whole square, which is nothing but your sigma nm square. Here n stands for noise, okay, not that thing. Okay, and then you have this, if m is not equal to n, then this simplifies to, or this expectation productifies, that is eta m of t into expectation of eta n conjugate of t. Now since both of these are zero mean random variables, this product comes out to be equal to 0. So therefore your sigma square is basically summation m equal to 1 to m summation n equal to 1 to m e power minus j phi m into e power plus j phi n into sigma n. I'll just write this as capital N for the sake of, yeah, just to avoid confusion. Yeah. Into delta N minus N. So therefore this comes out to be equal to basically summation m equal to 1 to m sigma n m square. That's all. So this is the value of your sigma square. So whenever your m is not equal to n, that summation terms will die down. So only m equal to m equal to n term will survive, and that, and at that point this quantity also becomes 1. So therefore this is the noise that you will get. So now if we substitute it back in this particular SNR equation, so therefore your gamma cophase is basically equal to your summation I equal to 1 to m alpha alpha m square es divided by summation m equal to 1 to m sigma capital N m square. Now what we wanted to find out? We wanted to find out average SNR. So we are asked to find the average SNR for cophasing. Okay. So therefore your gamma cophase, which is basically your average SNR, that is average of cophase, gamma cophase, this is basically equal to expectation of summation m equal to 1 to capital M alpha m square into Es divided by summation m equal to 1 to capital M sigma n m squared. Now let us just focus on this term. So your gamma cophase, capital gamma cophase, okay, not that. Yeah, so your expectation of summation m equal to 1 to capital N alpha m squared. This you can write as expectation of summation m equal to 1 to n summation n equal to 1 to, this is m alpha n. Okay. Now I can separate it out into two summations. So first one is summation m equal to 1 to capital M alpha m square. So this is the case where my m is equal to n plus summation m equal to 1 to n plus summation n equal to 1 to capital M for n not equal to m alpha m alpha n. And yeah, you have an expectation here. Now we had initially seen that expectation of alpha I square is 2 sigma I square. So this quantity here, this is basically equal to sigma m square, 2 sigma m square. And this, since alpha m and alpha n are independent, this we can write as expectation of alpha m into expectation of alpha n. This quantity is equal to under root pi by 2 into sigma m, and this is equal to under root pi by 2 into sigma n. So this basically comes out to be equal to pi by 2 sigma m into sigma n. Okay. So now if we substitute it here, so we get 2 times summation m equal to 1 to capital M sigma m square plus pi by 2 summation m equal to 1 to capital M summation n equal to 1 to capital M n not equal to m sigma m into sigma n. Now, if I now we have this expression here. Now let us substitute it back to our average SNR. So therefore, your average SNR of co-phase comes out to be equal to, you have your ES, then 2 times summation m equal to 1 to capital M sigma m square plus pi by 2 summation m equal to 1 to capital M summation n equal to 1 to capital M n not equal to m sigma n divided by, we have summation m equal to 1 to capital M sigma nm square. Okay, so this is the SNR, this is the average SNR when your channels are independent but not identically distributed, even the noise. Okay, now what we will do, we'll relax it and we'll make some things, some assumptions, that is all antennas are IIT, which means they are independent. Already they were independent, which means sigma m is equal to sigma for all I, for all m in 1, 2 and so on till capital M, and all the noise are IID, which means that sigma nm is equal to sigma n for all m. So for this, your gamma cophase, it comes out to be equal to ES into 2 times, you have sigma m sigma square. Sigma square is getting repeated m times, so you have 2m sigma square plus pi by 2 sigma square. Now this summation is repeated m minus 1 times, so this summation runs from n equal to 1 to capital M, but it is excluding one term which is for n equal to m. So this summation basically has m minus 1 terms, and these m minus 1 terms are inside another summation which has m terms. So therefore the total terms in this particular summation are m into n minus 1. So you have m into m minus 1, yeah, divided by m into sigma nm square. So I can cancel out this m from here, and then I can take out 2 sigma square common. Yes, by sigma nm square, we have 1 plus pi by 4 into m minus 1. And this particular thing is the SNR for one antenna, that is gamma 1. So therefore your gamma cophase is equal to your gamma 1 into 1 plus pi by 4 into m minus 1. Now if you remember, if you recall what we have done in the lectures or in the class, our m was equal to 2, and for that we had got our gamma cophase as gamma 1 into 1 plus pi by 4. Any questions? So this is all about the average SNR for co-phasing. Co-phasing combining scheme. If this is clear, then I will move on to the other part for optimal combining. Okay. This is clear. Then I'll move on to the second part of this question. We want to repeat the same thing for optimal combining, or what we call as the MRC. And for MRC, we had earlier also discussed, the gamma MRC, or basically what we do is we construct our signal, or we combine our signal something like this: m equal to 1 to capital M Gm into our m of t, where this Gm is basically given by Zm conjugate divided by sigma noise at mth antenna square, not square, this. So therefore your gamma MRC comes out to be equal to, let's do it in a good way. So this is equal to summation m equal to 1 to capital M. You have your Gm into Zm S of t plus eta m of t, which is equal to summation m equal to 1 to capital M Gm into Zm S of t plus summation m equal to 1 to capital M Gm into eta m of t. Now we had seen that your gamma MRC is magnitude of summation m equal to 1 to capital M Gm into Zm square into Es divided by, now this is the weighted, so this is basically adding IID Gaussians with variance magnitude Gm square into sigma nm square. So this is summation m equal to 1 to capital M magnitude of Gm square into sigma nm square. Okay. Now your Gm was optimally obtained as Zm square upon sigma nm. So let us substitute that. So gamma MRC is equal to magnitude of summation m equal to 1 to capital M Zm conjugate upon sigma nm into Zm. There should be a square here, I think. Yeah, sorry. Yeah, there should be a square. Into Es divided by summation m equal to 1 to capital M magnitude of Zm square upon sigma nm to the power 4 into Znm square. This gets cancelled, and what we are left with is basically summation m equal to 1 to capital M magnitude of Zm square upon sigma nm square whole square into Es divided by summation m equal to 1 to capital M magnitude of Zm square upon sigma nm square. This cancels, and what we are left with is gamma MRC equal to summation m equal to 1 to capital M magnitude of Zm square into Es divided by sigma nm square. So this is your instantaneous SNR essentially. Okay, so now what you want to do is want to find the gamma MRC, capital gamma MRC, which is your average of this quantity, that is average SNR, that is expected value of your gamma MRC, which comes out to be equal to summation m equal to 1 to capital M expectation of magnitude of Zm square into Es upon sigma nm square. And this magnitude is this thing is basically expectation of magnitude of Zm is alpha, so alpha m square, which is basically equal to 2 times sigma m square. So this is equal to summation m equal to 1 to capital M 2 times sigma m square into Es by sigma nm square. So this is essentially your m equal to 1 to capital M gamma I, gamma M. Now again, if your antennas are identically distributed, that is if sigma m square is equal to sigma and sigma nm square is equal to sigma n square for all m, then your gamma MRC becomes m times 2 times sigma square into Es by sigma n square, that is m times gamma 1. So this is what we had seen in the class. I just repeated it so that these kind of calculations are understandable to you, and if something similar comes up with random variables and other stuff, you are capable of doing it. Any questions? Okay, if there are no questions, then let me move on to the next question. Okay, so this says that if selection combining is used and k out of m antennas are weak, how will the outage probability scale with the average SNRs? Okay, so let us first go back and see the outage probability expression that we had written for selection combining. Yeah, so this was the outage probability for the Rayleigh case that we had written for the outage probability. Okay, so let us take up from this point. So this is the from this particular part. So from question 5, for Rayleigh faded channel, the outage probability is given by product of I equal to 1 to capital M 1 minus e power minus gamma th by capital gamma I, where gamma is the average SNR for the ith antenna. Now what it is said is that k out of m antennas are weak. So what does it mean? That let's say without the loss of generality, gamma 1 to gamma 2 and so on till gamma k, these are having much less SNRs, which are much less than gamma th, and let's say this is, and for this we'll use the notation gamma, this one, and for the remaining, that is gamma k plus 1 and so on till gamma m, this is much greater than gamma th, and let's say we'll denote this by simple capital gamma. So therefore the probability of outage, in the lecture we had seen it for one antenna being weak. For now, for this particular we are taking k. So we'll have probability of I equal to 1 to m, 1 to k. Let us separate it out. 1 to k, 1 minus e power minus gamma I by gamma 1, since they are IID, into product of I equal to 1 to k plus 1 to m, 1 minus e power minus gamma sorry, by gamma. Okay. Now what we basically have is e power minus x as 1 minus x plus some higher order terms. So for large SNRs, those higher order terms we can completely neglect. And that if we substitute and that using that, this particular equation 1 minus e power minus gamma th by capital gamma is basically equal to 1 minus gamma th by gamma, which is equal to gamma th over gamma. Okay, and similarly here your gamma th is much greater than your gamma 1, which means that this particular quantity is 1 minus approximately equal to 1 minus 0, which is equal to 1. So therefore your probability of outage comes out to be equal to 1 into 1 minus, or rather gamma th by gamma, and this product is over I equal to k plus 1 to m. That is, you basically have m minus k terms. So this is gamma th upon gamma to the power m minus 1. So what we were asked is, how does this outage probability scale with the SNR? So what we are seeing is the outage probability is inversely proportional to gamma to the power m minus k. So these weak antennas are basically degrading the performance or degrading the outage probability. So the slope is reduced now. If we take the logarithmic scale, the slope is lower. So it will decay slowly. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay. Yeah, so this is what we have. So this question says that find the MGF. MGF is what? Moment generating function. We had seen this in last week. Of the SNR of the MRC. Okay, so we want to find the moment generating function for the SNR of your MRC scheme. So let us go back here and let us stay here for 1 minute. So this was the instantaneous SNR of your MRC scheme. Now this factor here is basically your gamma m, which is the instantaneous SNR instantaneous SNR at mth antenna. So this is basically equal to summation m equal to 1 to capital M gamma m, where gamma m is an exponentially distributed random variable with mean capital gamma m that we had already seen. So for 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 MRC, the instantaneous SNR is given by gamma MRC which is equal to summation m equal to 1 to capital M into gamma m, where this gamma m are exponential random variables with mean capital gamma M, and these are independent. Okay. So therefore, the moment generating function psi MRC or psi gamma MRC of S is basically expected value of e power minus, sorry, not minus, e power gamma MRC S. Now let me substitute gamma MRC here. So this is expected value of e power summation m equal to 1 to capital M gamma MRC gamma M into S, which I can write as expected value of product of m equal to 1 to M e power gamma M into S, which is equal to, now since gamma m's are independent, I can push the expectation inside the product. So this is equal to product of m equal to capital m equal to 1 to capital M, expected value of e power gamma ms, and this thing here is basically, yeah, this we did because since gamma m's are independent. So okay, so this is what we have. So this is equal to product of m equal to 1 to capital M, the MGF of gamma m evaluated at S. This is the first thing that we have. Next thing, now let us evaluate this psi of gamma m of S, which is basically expected value of e power gamma ms, which is nothing but integral from 0 to infinity e power gamma ms into f of gamma m d gamma m. This thing is equal to integral 0 to infinity e power gamma ms, and PDF of this is 1 over capital gamma into e power minus little gamma m by capital gamma m d gamma m. This 1 over gamma m, I can take it outside, then I have integral 0 to infinity e power minus gamma m, I can take common, then I am left with is 1 over gamma m minus s d gamma m. So this is equal to 1 over gamma m into e power minus gamma m into 1 minus gamma m minus s divided by 1 over gamma m minus s minus sign from 0 to infinity, and this is valid when 1 over gamma m is greater than the real part of s. This is the region of convergence that we have, and this comes out to be equal to 1 over gamma m into 1 divided by 1 over gamma m minus s, which is equal to 1 over 1 minus gamma m into s for your real part of s less than 1 over gamma m. Okay, so this is the moment generating function for the SNR at the mth antenna. Now if I substitute it back in this particular equation, I'll get the MGF for the SNR for your MRC. So let's do that. So therefore, psi of gamma MRC of S comes out to be equal to product of m equal to 1 to capital M. We had it at psi gamma m of S, which is equal to product of m equal to 1 to capital M, and you have psi of this thing as 1 over 1 minus gamma ms, where this is valid when real part of s is less than gamma m, 1 over gamma m for all m. Okay, so this is the moment generating function for gamma MRC, and a special case is if gamma m equal to gamma for all m, then this gamma MRC, psi of gamma MRC of s turns out to be equal to 1 over 1 minus gamma s whole to the power m, and this region of convergence will become real part of s to be less than 1 over gamma. Is it clear? Any questions? Okay. Okay, if there are no questions, let me move on to the next question. Let us try to use that particular thing, MGF that we have derived to or let us see how it is useful. So now it's said that assume we have a non-coherent BPSK modulation scheme, then find the probability of error if we use that scheme for an in an MRC kind of situation. Okay, so the probability of error as a function of your SNR, that when for a given SNR value, or what we had referred it as for an AWGN channel, the for non-coherent BPSK, this comes out to be equal to half of e power minus gamma MRC by 2, and the probability of error in MRC will be equal to expected value of probability of error gamma MRC, which is equal to integral 0 to infinity probability of error of gamma MRC into PDF. So, or in other words, yeah. So this is what we will be doing. But what I'll do, I'll directly use this particular equation. So this I can write as expected value of half of e power minus gamma MRC by 2. So this half I can take outside, half into expectation of e power. I'll write it in a little bit different fashion. I'll write it as gamma MRC into half, minus half. And this is basically equal to half of expected value of e power gamma MRC s into s evaluated at s equal to minus half. So this is basically equal to half of your moment generating function of your gamma MRC into minus half. Okay, so now what was the gamma MRC we have derived? We had found out to be equal to this thing. So now let us substitute it here. So this is half of product of m equal to 1 to capital M, and this psi of this came out to be equal to 1 over 1 minus gamma m into s. So this is 1 over 1 minus gamma m into s is now minus half, and this s very well lies in the region of convergence because this is a negative value and your average SNR is going to be a positive quantity. So therefore this lies in the region of convergence. Okay, so therefore this comes out to be equal to half of product of m equal to 1 to capital M 1 over 1 plus gamma m by 2. Now same thing, if gamma m is equal to gamma for all m, then probability of error in MRC comes out to be equal to half of 1 over 1 plus gamma m by 2 whole to the power m. Is it clear? Any questions? If not, then let me move on to the last question for today. So in the class we had said that the dense method is capable of generating uncorrelated waveforms, and for that what we had done was, so the dense method, how it works is, for dense method what we do is we have this z of t as summation n equal to 1 to n naught cos of, or rather let me write it as a n of t, which is also equal to 1 1 and so on till 1 into a1 of t, a2 of t into a n naught of t, where a n of t is basically cos beta n plus j sine beta n into cos of 2 pi fn t plus phi n. For notational simplicity, I'll just write it as e power j beta n into cos of 2 pi fn t plus phi n. And then we said ki to generate some n naught values, what we will do, we'll use the Walsh-Hadamard matrix. So we'll generate it something like this. We'll have z1 of t, z2 of t, and so on till zn naught of t, which will be equal to your Walsh-Hadamard matrix of dimension n naught times n naught into a1 of t, a2 of t, and so on till a n naught of t. Now we said that this vector is basically uncorrelated. Okay. So let me say that this is basically z equal to h into a. And this H is a Walsh-Hadamard matrix. This is a Walsh-Hadamard matrix, and this is a unitary matrix. That is H into H Hermitian is equal to H Hermitian into H is equal to an identity matrix. Okay, so now let us, so what do we mean by it being uncorrelated? This vector Z is uncorrelated if the time average, so let me write it as Z of t. Yeah, if the time average z of t into z of t Hermitian t plus delta t. Hermitian is an identity matrix. Not identity, is diagonal. If that is the case, then it is yeah, then it will satisfy whatever we need. So then only we'll get uncorrelated things. Yeah. So basically, if you are looking at different points like z1 of t and z2 of t plus 1 or t plus delta, then these two should be uncorrelated for all t1 and t2, or for all delta t's. Okay. So now let us see this. So now you have z of t into z Hermitian of t plus delta t, which is equal to z of t is what? H into a of t into a of t plus delta t Hermitian into h Hermitian. So we want to find the time average of this. H doesn't depend on anything, so we'll have on time. So we have it something like this. So now let us look at this matrix. I'll just name this matrix as A bar. So this A bar of, let's say, delta t. So this A bar of delta t is essentially the time average of A of t into A Hermitian of t plus delta t. And if I look at its m comma nth entry, then that is given by A bar of delta t m comma nth. That will be basically time average of A bar of t, its mth entry, into A bar of t plus delta t, its nth entry conjugate. So this is basically am of t into an of t plus delta t conjugate. So what is this am of t into an conjugate of? Am of t is basically e power j beta m into cos of 2 pi fmt plus phi m, and an conjugate is e power minus j beta n into cos of 2 pi fn t plus 2 pi fm fn delta t plus phi n. Okay. So this thing is equal to e power j beta m minus beta n into time average of cos of 2 pi fmt phi m times cos of 2 pi fn t plus 2 pi fn delta t plus phi n. Okay, so this is what we have now. Now, when we were discussing a question today, we were looking at the time averages. Yeah, so we saw that when we have two different frequencies and we want to take the time averages, and we have two cost functions, yeah, like this, then that particular thing comes out to be equal to 0. So time averages, when you have cos into cos with two different frequencies, that comes out to be equal to 0. So in this particular question here, yeah, so we have case 1. m is not equal to n, then this particular thing, that is the time average, is equal to 0. So therefore your a bar of delta t is m comma nth entry comes out to be equal to 0. Now in case 2, when m is equal to n, this a bar of delta t m comma mth entry is equal to e power j beta m minus beta m, which is basically equal to 0. So it comes out to be e power j 0 is 1 into cos of 2 pi fm t plus phi m, so plus here, times cos of 2 pi fm t plus phi m plus 2 pi fm delta t. Now we can apply cos A cos B formula, and this is basically 1. So we'll have cos A cos B. If we apply, that will be half of cos of 4 pi fm t plus 2 phi m plus 2 pi fm delta t, plus we have cos of A minus B. So in this part and this part is common. So if we subtract these two quantities, we will be left with only this. So plus cos of 2 pi fm delta t. Yeah. So now what I'll do is I'll separate it out. So I'll have half of the time average of cos of 4 pi fm t plus 2 phi m plus 2 pi fm delta t. So this is a sinusoid which is varying with time, and plus we have half of cos of 2 pi fm delta t. This is a constant, does not change with time, so its time average is same as that quantity. Now again, this is a sinusoid with frequency 2 fm and phase as this quantity. So if we want to have the time average of this thing, that will come out to be equal to 0. We had seen it earlier. So this quantity is equal to 0. So what we have now is this comes out to be equal to half of cos 2 pi fm delta t. So now if I substitute it back in this particular equation here, that is a, so this thing a bar of delta t is basically a diagonal matrix with its mth entry given by this quantity. So your a is basically half of a diagonal matrix with its entry given by cos of 2 pi f1 delta t, cos of 2 pi f2 delta t, and so on till cos of 2 pi fn naught delta t. Okay, now if I substitute it back in this Hadamard matrix, this particular matrix, in this matrix, that is time average of zt into z Hermitian t plus delta t. So this comes out to be equal to h into half of, or rather, so a of delta t bar h into a bar of delta t into h Hermitian. And if I look at its m comma nth entry, then that will be, so this h I can write as basically h1, h2, this h, and so on till hm. So this I can write as a bar let's do it in this way. So I'll have h1, h2, and so on till h of h Hermitian or what? Let's do it in the opposite fashion. Okay, something like this. Okay, now what we will do is, I think I have made some mistake here. I'll show this for delta t equal to 0. If at current time instant it is uncorrelated, it will be going to be uncorrelated throughout. So let's just look at for this quantity. If I have delta t equal to 0, then a bar of delta t is equal to half into an identity matrix. I'll get back to this. I'll solve it for a generalized case and post it in the group. I have lost the solution, it seems. So this thing comes out to be equal to h into half of identity matrix into h Hermitian, which is basically half of h into h Hermitian, which is equal to half into identity matrix. So since this is a diagonal entity, which means that zt entries are uncorrelated at all time instants. This thing will also come out to be uncorrelated, but yeah, I'm messing up a little bit. Yeah, but this is how you will be doing it. It will come out to be diagonal. I'll post the proper solution of this thing, a generalized case in the Q&A portal, or maybe in the next week I'll take up from this question, this part, and solve it again. Any questions till this point? This was all that I wanted to cover today. If you have any questions, then please let me know in any part of the tutorial. Any questions? Hello?
Madam, could you please tell me about the Doppler, how it will affect on the users?
Sorry, what? Your voice is cracking at my end.
Okay, madam. Madam, can you please tell me about Doppler shift when it is far away from the user or towards the user? Like
Okay.
that questions are coming, ma'am, in assignments. I am little bit confusion about that.
Okay. So, do you remember the Say and Vishwanath question with velocity? When the so okay, I'll try to explain it with the help of the David Say and Vishwanath example. Okay. So what we have a transmitter and we have, let's say, some receiver here, and this receiver is moving with velocity v away from the transmitter. So here the case one, it is moving away from the transmitter. Okay, the initial distance is some r, and now it will move in time t. It will move to a distance of r plus vt. Okay, it will move little bit here in time t, which will be v into t. V into t is the displacement or distance in covered in time t. So how will your electric field look now? So your electric field at time t will look at, if you're transmitting cosine waveform, doesn't matter. it will be some alpha over r plus vt into cos of 2 pi fc t minus your delay, that is r plus vt by c. Is alpha r plus vt cos of 2 pi. Now what I'll do, I'll combine the t terms together. Okay, fc into 1 minus v by c into t minus r by c, minus 2 pi fc r by c. Okay, so this is what you have, and this is your effective frequency, effective carrier frequency. So your fc is equal, or your f effective is equal to fc minus fcv by c, and we name this as fd. This is the notation that we are using. So your fc minus fd, and fd is a positive quantity. So which means that if you are moving away from your transmitter, you see a reduction in your carrier frequency, effective carrier frequency. Now let us do the opposite case. So you have this, you have a transmitter, you have a receiver. Now it is moving with a velocity v, but at a but it is moving towards. So now what will be the, okay, and the initial distance was r, and in time t it will be here, so the distance here will be r minus vt. So therefore the electric field that you will see now at time t will be basically equal to some alpha upon r minus vt into cos of 2 pi fc t minus the delay, that is r minus vt by c, which is equal to alpha upon r minus vt. Again same thing I'll do, 2 pi fc 1. Now you have a minus sign here and a minus sign here, so you get minus minus plus 1 plus v by c into t minus 2 pi fc r by c. Okay, now in this situation your effective carrier frequency is basically fc plus fcv by c, that is fc plus fd, which means your carrier frequency, effective carrier frequency, is increased when you're moving towards the transmitter. Does it make sense to you now? So
Yes, madam.
whenever you get
Uh,
confused, just take up this example and solve it, because that's how I do. Any other
mm,
questions?
no, madam. Thank you, ma'am.
Yeah.
No, madam. Thank you, madam.
Yeah. So if you don't have any other questions, then you can uh, leave the meeting. Thank you for attending today's session.